Okay, so today we are going to perform an experiment based on op-amp, that is op-amp based integrator and op-amp based differentiator. I will just share my screen and then we will start. Okay, I guess my screen is visible to you all. Let's see where I have stored the write-up. Industrial electronics, op-amp. Okay, so simultaneously I will start Proteus. Yes, in demo. This is the circuit diagram already given in the write-up for integrator as well as differentiator. Now, what we have to do is connect the waveform. First, you connect a square wave at the input of the integrator and see if you are getting a triangular wave. Similarly, build a differentiator, connect a square wave at the input and see if you are getting pulses or not. Okay. So I will start performing this file, new project. So it will open a wizard where you just have to click next, 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 next. So click next, 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 and finally click finish. Okay. So let me start with the integrator. First, you go to the component mode, select place, and now we have to place op-amp IC, which is 741. So it will show you 741 op-amp. Click OK and then place it. Okay, you can place it in the center if you want, so that you can optimize the maximum area. Now, next thing you have to click on place component. Next thing we want to place a battery. So let's go and place battery. This is for the supply of the op-amp. So now we want to connect plus 15 volt at pin number 7 and minus 15 volt at pin number 4. So I will need two batteries. Now to change their voltage, double click on this 12 volt and make it 15. So for any op-amp experiment, this is a basic setup that we have to do. That is giving a VCC and minus PE. Next thing we want to place ground. We can have a common ground for entire circuit so that it is easy for us to connect everything to the ground. So first supply negative terminal goes to ground, then plus 15 volts goes to pin number 7. Next, the positive terminal of the second supply goes to ground, and then negative terminal goes to pin number 4. So this is a basic op-amp supply connection. And now we want to continue with the integrator circuit. Same thing you have to do for the differentiator. So let me go and check in the write-up. What are the values we need? Let me just zoom in. I will share this write-up on Classroom as soon as we finish. Um, so next is I need a resistor of 10K, 100K and capacitor of 4 nanofarad. So let's go back to place component. Now don't forget to change it to always a component mode and then click place. And here you can type resistor and you can choose 1K 10 watt resistor initially and then you place it. So one register goes in the feedback loop. So from output pin number 6 to input pin number 2, and one register goes at the input. Now whether to give input at pin number 3 or 2, we will just verify. Input is given to pin number 2 itself, so it's a inverting integrator, and that is given through a register of 10k. This is 100k, and then we need a 4 nanofarad. So let me just change the value by double clicking this 1k and making it as 10k. Okay, and then it's a inverting, so I will just connect it to pin number 2, and pin number 3 must be grounded. Now next thing is you have to change this value to 100k, so I will just change it to 100 and click OK. Next component needed is capacitor, so again go to components, place component, and type cap. You can choose any capacitor right now. Then we will change its value. So it's 1 nanofarad right now. I will just connect the capacitor in parallel to the resistor that we have. And now I will change its value. So if you double click on the value, it will allow you to change. But by mistake, if you are double clicking on this, you will not see any option of changing the value. Now next is seeing the input. We need an oscilloscope. So go to the instrument, select the oscilloscope here, place the oscilloscope. Now we will monitor the input on channel A. For input, again we have to go to something called a generator. Select any generator. It's okay. We will start with square wave, so pulse generator, and then feed it to the input. At the same time, you will connect channel A at the input. And I want to see the output at channel B, so I will connect channel B at the output. Next thing, you have to double click on this pulse. Check the pulse voltage high is 1 volt, and we want to frequency as 1k. So let's take it 1000 and click OK. So now the circuit for integrator is ready. That is first part of our experiment, and we will run the simulation. So as soon as you run the simulation, you will see that input in yellow is a square wave, and output is in blue, which is a triangular wave. Now to measure the amplitude and voltages, you can change this knob to, ideally you can put it to 1 volt so that there is no multiplying factor, and measure the height of this. To measure the height of this, you have to align it to one of the axes, and then you can measure. So if you align it properly, you will see the yellow line will be just 1 volt. Now coming to the blue line, again you can keep it at 1 volt, and you will see that it has got gain also. And to measure the magnitude, you have to count number of divisions like 1, 2, 3, 4, 5, and almost 6, 5.8. So 5.8 into 1 volt, that will be your output. Next thing, to measure time, you can just change this time axis, and again, to rotate the time domain response, you have to align it to one of the horizontal, and 5 into uh, zero point 0.2. So that will be around 1 millisecond, because this is a millisecond. So 1 millisecond upon 1 is 1 kilohertz. So frequency output and input frequency is same. Uh, and this is how your first input in the reading diagram comes. Like integrator, square wave, we have applied 1 volt input uh, with frequency of 1 kilohertz. The output is somewhere around 5 point, I guess, 8, and F out was again 1 kilohertz. Next thing, we have to do a frequency response for the integrator. For that, you have to open a software called Excel. Uh, Now, those who don't have Excel can use online tool for plotting called Plotly, or any other tool which is open source and free to plot the graph. Once you open the Excel, what you have to do is enter the frequency on one side. We start with 1 hertz, then 10 hertz, and go up to 1 megahertz. So next will be 100 hertz. Next is 1000 hertz, then 10,000 hertz, then 100 kilohertz, and then finally 1 megahertz. So this is how we are going to plot, and against that we are going to measure output voltage V out every time. So let's start measuring. I will take the first reading for you and then you can continue. So for first reading, so if by mistake you close the digital oscilloscope and then if you stop and rerun the simulation, the oscilloscope won't appear again. So you have to go to the debug and find the digital oscilloscope window so that it will come back. Next thing we have to do is change this square wave input to sine wave, because as per your reading table, only the first reading is for square wave. Next onwards, all are sine wave. So I will change it to sine wave. What I am doing, just observe this. You just have to stop the simulation first. You have to double click on this and just change this to sine wave. Again, it amplitude is 1 hertz. Frequency, you have to start with 1 hertz. So I will just put it at 1. But if you can start at 1 kilohertz, that is also fine, because our time division knob was tuned for 1 kilohertz. And then you can reduce and increase. So just run the circuit again. Since I closed the CRO, I will restart the CRO from digital oscilloscope. Now for sine wave, your output is looking like a sine wave only. There is no difference in sine wave. Only the phase shift has occurred because the integration of sine is, I guess, cos. So that's why the cos wave also looks like a sine wave, but phase shifted. That's the only thing happening here. And next thing, since it was perfectly tuned, you got the perfect response. But as you change the frequency, you have to change this amplitude on time, both knobs, because this filter, if you have focused in the lecture, I have taught you that integrator also act like a certain kind of filter. And if you see its frequency response, you will realize that it passes lower frequency and stops the higher frequency. So integrator is also acting as a low pass filter. So let me take one reading for you. Let's say at 1 kilohertz, I want to measure the amplitude. For amplitude measurement, you can ignore the yellow line because we just want to measure the output amplitude. Input amplitude will be 1 volt as you have set it. And then you bring it to any of the lines, align it perfectly and start measuring. So it's at 1 volt per division and I have 1, 2, 3, 4, 5, 6, 7.2. So I am getting reading at 7.2. Go to your Excel. For 1 kilohertz, the reading is 7.2. Obviously, your reading and everything will change, but whatever reading you are getting, you can write there. No issues. Next is, let's say I want to, now frequency will remain same that you have already verified. But if you want to cross verify, you can change the time domain axis and still measure the frequency also. Next thing is how to change the input waveform. So I will just stop the simulation. Now I want to take a reading for 100 hertz. So I will change this frequency to 100 and click OK. Again, if I run, see, because of the time domain, you get this weird kind of waveform. So first thing, you have to correct it for time domain. Since the magnitude has increased, you have to change this to also some high voltage value. And now if you assign this one, this goes like 1 division, 2 division, 3 division, 4 division into 5 volts. So I'm getting 20 volts for 100 hertz. So as per the reading table, I should get 20 volts for 100 hertz, which is, where is 100 hertz? Okay, everything is in kilohertz. So zero point 0.1 kilohertz is nothing but 100 hertz. Last time I got 19.4, today I'm getting 20. So it depends on what kind of or how precise I am measuring. As per the circuit, nothing changed. So the readings of entire batch should be same. But at the same time, if you miss any connection or if you didn't measure it correctly, your readings might vary here and there. If there is large mistake, then you must have missed some of the connections. Or a common mistake that students do is changing these values to proper values they are not doing, and they are keeping 1k 1k and 1 nanofarad by default values, and that's why they are getting different errors. So I will stop this recording now, and if you have any doubts you can ask me.